Hey guys, welcome to another video of quantum field theory, and today we'll be summarizing what we've talked about in quantum field theory 2. So, in quantum field theory 2, our main focus was on quantizing our fields. So in quantum field theory 1, we talked about the Klein-Gordon equation, the Dirac equation. We were just basically solving equations, right? But there wasn't really much meaning into what we were doing. In second quantization, we bring meaning into our fields. They now have dynamical roles. So here's the Klein-Gordon equation. You solve it and get this as our answer. And for second quantization, what we do here is that we take our creation and our annihilation operators and we put it into a commutator. And we define it as being this over here. And this is our starting point for quantum field theory. We take this as a postulate, and as a result, the creation and the annihilation operators actually become creation and annihilation operators, basically. So before, they were just like momentum modes, they didn't really have much meaning, but now they are operators, and they have a dynamical role in quantum field theory. There is a closely related concept in quantum mechanics. We can take the commutator of x and p and set that equal to I h bar. And as a result, the position and the momentum become operators. But it's still very distinct from quantum field theory, though close, because this operator, the momentum operator, for example, is going to act on the wave function or give us an eigenvalue, where that value is the momentum. But in quantum field theory, A conjugate K, we don't really care. Well, we kind of do care. We can also act on some wave function with a conjugate K, and it can give us an eigenvalue. That's called a coherent state. But instead, we're more interested in how it acts on the vacuum state, a state with no particles. And this will actually give us a state with one particle with momentum K. It is in this sense that quantum field theory can be said to be more mathematically fundamental than in quantum mechanics. Because in quantum mechanics, we kind of already deal with the particle states from the get-go without formally deriving them, if that makes sense. But in quantum field theory, we actually kind of build these particle states from the groundwork itself, from the vacuum, which we don't really do in quantum mechanics. So we can look at K1. A conjugate K1 acting on the vacuum state gives us one particle with momentum K1, where K1 is some specific momentum. And then A conjugate K2 acting on the vacuum state will give us one particle with momentum K2. It's pretty intuitive how this works. We can look at A conjugate K1 acting on A conjugate K2 acting on the vacuum state. That gives us one particle with K1 and one particle with K2. So we see that in quantum field theory, we have a very elegant way, building up different particle states. And we call the collection of all these different states with all these different particle numbers, we call that a Fock space. And these creation and annihilation operators, they're like ladder operators. They allow us to move along this Fock space. Now, an important thing to mention here is that the field itself also becomes an operator in quantum field theory. The field is often compared to the wave function in quantum mechanics, but this is kind of like a mistake, because the wave function in quantum mechanics is not an operator. But in quantum field theory, the field is an operator. It's going to act on the vacuum state, and it's going to give us a kind of a weird state. The state that it gives us is kind of like a position eigenstate, but it isn't exactly one. But we kind of call it one. It's kind of weird. I explain it more in my propagator video, but it's kind of like a position eigenstate, at least for long or for large distances. Carrying on with this analogy where the field kind of creates position eigenstates-ish, we can look at the probability amplitude that some particle travels from xt to x prime t prime in space-time. And we call this amplitude the propagator. And this is something that exists in quantum mechanics as well. But it's nice to be able to calculate it in quantum field theory too. We can also look at the probability amplitude that the particle starts at xt and goes to x prime t prime if t prime is greater than t. So if t prime and x, so if t prime is in the future, basically. And then we can look at the opposite for if t prime is less than t. And we call this over here the Feynman propagator. Now, I know that this amplitude might look weird to you guys. Like, why do we care about this over here? And the reason is that we care about it because this propagator shows up a lot in interactions. It turns out that the Feynman propagator is what's called a Green's function of the Klein-Gordon equation. So when we start doing interactions, it's going to pop up a lot, which is why we first address it here. So right now it's not very useful for us, but later down the road it will become pretty useful. We can also calculate the Feynman propagator by using the path integral, but since we are doing canonical quantization, we are not going to discuss this path integral yet, though we will in the future. So just like in quantum mechanics and in all of physics, we have what's called a Hamiltonian. This Hamiltonian is going to be an operator again, because since these are operators, it makes sense that the Hamiltonian is also an operator. It's going to act on some state and give us the energy of that state. Problem is, though, that when you do this in quantum field theory, you get infinity as your answer. So what we can do is we can restrict ourselves to the vacuum to make this discussion much more simpler. Here is a Hamiltonian, but for a vacuum. So this Hamiltonian is going to act on the vacuum state and give us the energy of that vacuum state. Problem is that this also is infinity. Yay, right? But actually this should be a delta of 0. But if we kind of pretend that this delta does not exist, or by using some volume arguments, we can make it go away. The problem is, though, is that we still get infinity as our answer. So what we can kind of say is that, oh, well, maybe if the Hamiltonian is divergent, maybe if we compare different values for the Hamiltonian, we can get a finite value. It sounds dumb, but it kind of works. I'll show you guys how. And we kind of see this in the Casimir effect. So in the Casimir effect, we have two long plates, and basically we calculate the quantum field inside the plates, and we see that inside the plates, the number of modes is quantized, it's discrete, but outside of the plates, the quantum field can be breakdancing, it can be doing anything it wants to, as long as it obeys the Klein-Gordon equation, and as long as it goes to 0 at the plates. And essentially, since there are more configurations of fields outside the plates compared to inside the plates, there is a net force that pulls the plates inwards to each other. We call that the Casimir force, where the force is equal to, I think it's minus pi over 12a squared, where a is the distance between the plates. We calculate this in our, we actually discussed this more in detail. But the more basic idea here is that the energy on the outside is infinity, and energy on the inside is also infinity. And if you subtract those infinities in a particular way, you get a finite value, which causes the plates to attract towards each other. And whether or not you buy the argument is up to you, but that kind of leads to the Casimir effect. There's much more to this effect. There's a lot of debates around it, but I encourage you guys to check those all out. The Casimir effect is just one example of how differences in vacuum energies can play a physical role. So, yeah, cool. For spinors, we pretty much do the exact same thing. Spinors obey the Dirac equation. We get this over here, and then this CSK, this should be a conjugate. These things are like the creation and the annihilation operators, but for spinors instead, CSK is going to act, or C conjugate is going to act on the vacuum. It gives us one particle with spin S and momentum K. DSK, there's also separate relations for DSK, but you guys already know them probably. So DS conjugate K is going to act on the vacuum state and give us an antiparticle. So it's one particle with momentum K, spin S, but it's an antiparticle because this particle has the opposite charge. But yeah, here's the Hamiltonian for spinors. If you were to, we see that there's a plus sign here, right? It's a plus sign. So this means that if we were to act on the Hamiltonian by some antiparticle state, so D conjugate SK acting on the vacuum state, it's actually going to output a positive energy as an output because we have a plus sign here. It does not discriminate between spinors and anti-spinors, but the charge operator, on the other hand, we will have a different answer. So antiparticles are just particles, but with different charges instead. I kind of cleaned up the Hamiltonian there in this. I hope that's a bit more easier to read, by the way. It's also nice to see how curved space-time changes things up a little bit. So here we have the number operator. In flat space-time, we have this for the Klein-Gordon equation. This is technically true in curved space-time as well, but certain classes of curved space-time that aren't super weird. The main idea here is that G mu nu, the metric tensor, can be different in different coordinate systems. So here's the Minkowski coordinate system, and then here's the Rindler coordinate system. So basically, we'd be plugging in different metric tensors, basically, for all these different coordinate systems. And as a result, the actual Klein-Gordon equation will be kind of different, at least at first glance. And here I have written out the Minkowski coordinates and the Rindler coordinates. You guys can see the horizon, the lights-like horizon. And the Minkowski observer will use A conjugate K and A of K. The Rindler would use B conjugate P and B of P. These to find different vacuums. And as a result, they disagree, which leads to the Unruh effect / the Hawking effect for curved spacetime. So the Unruh effect happens in flat spacetime, to be clear, but analogously, we can extend this concept in curved spacetime, and we get the Hawking effect, which is pretty cool. But some of y'all might say, wait a second. The Hawking effect deals with a collapsing sphere that scatters some spherical modes. So what's going on here? Now, there is technically two different kind of concepts that are also called the Hawking effect. We looked at the Hawking effect where we compared two different observers. But in the original calculation, what was done was a single observer was compared at different times, basically. And we have a collapsing sphere that becomes a black hole. Essentially, the quantum field around that black hole will kind of become scattered. It becomes a bit weird. And as a result, for late times, we actually see particles around where the inertial observer initially saw as empty space. There are two different kind of concepts also called Hawking. We call the Hawking effect. We explored one of them. We still got the same Hawking temperature, but just in different ways, kind of, if that makes sense. So we'll be exploring this alternative derivation for the Hawking effect in a future video, once I fully understand it myself, I guess. Also, we can look at QFT in an expanding spacetime. We know that for an expanding spacetime that expands, there is also a horizon called a cosmological horizon, which also releases its own horizon radiation. We can solve for that too, but that will also be in a future video. But yeah, but the basic idea here is in curved spacetime, different observers tend to disagree on the number of particles. These disagreements make up for a lot of effects. Now, how can we actually explain the Unruh effect from the inertial observer's perspective? Because remember, that accelerating guy, the accelerating pony, Rainbow Dash, she will see a lot of particles in the vacuum, and as a result, she will see a temperature. If she carries the glass of milk, the milk will heat up. So that's one way she can warm her milk in a vacuum, I guess. But how would Twilight explain that? How did she explain that at all? Well, this is where quantum field theory for interactions comes in. The quantum field theory that we've been doing so far was the quantum field theory for free fields. I've said this word a lot, free fields. What does it mean? Well, a free field is just a field that does not interact with other fields. That seems like a truism. It is, but I'll explain more in the next series, which is all about interactions. But basically, it's kind of like how in classical mechanics, we have a Lagrangian, And here is the Lagrangian for a free particle. This is a particle that does not have any forces acting on it. So it does not collide with any other particles. It does not slow down or speed up. There's no interactions at all. To describe interactions, we add what is called a potential term, a non-constant potential term to be specific. And as a result, the particle can now interact with other particles. That's how it's done in classical mechanics. Similar thing in quantum field theory. Here's the Lagrangian for a free scalar field. And like before, we can just add a potential term on here that's a function of phi inside of x, and then we can have interaction. So the free scalar field, just this part of the Lagrangian, it describes particles like pions, Higgs bosons that do not interact with each other. So this basically means that our particles can never collide with each other. They can't bounce off of each other. There's no cross sections. There's no decays, and this kind of makes sense, right? Because remember that our number operator in quantum field theory, if you actually do the calculation yourself, you'd actually find out that the number operator commutes with the Hamiltonian. And because of Ehrenfest's theorem, this implies that the number of particles for a free field is always conserved. So there's no interactions happening. We can't create particles. We can't destroy particles. I know that it's kind of like confusing because you have creation and destruction operators, but those operators don't describe a physical creation. They just mathematically describe a larger amounts of particles, if that makes sense. We can better illustrate this by writing down the Lagrangian for a system with spinor particles and scalar particles. So this Lagrangian right over here, there's no interactions happening at all. If we were to chuck this Lagrangian into the order of the Lagrange equations and crank out the math, we would get the Klein-Gordon equation and the Dirac equation. But these were the same equations that we had beforehand. So the scalar field does not react to the presence of a spinor field, and the spinor field does not react to the presence of a scalar field. So a scalar field does not interact with the spinor field, right? So we call each of these fields free. An electron and a Higgs boson won't collide with each other. However, if we add some interaction term, perhaps, that kind of mingles these fields together, like, say, I don't know, this over here, I just made something up, where G here is some interaction coupling, and we have multiplied these two fields together. Now we have interactions, because this term over here, we can now describe electrons colliding with the Higgs boson. We can now describe things like that because of this interaction term. And if we were to put this into the order of Lagrange equations, we would have coupled equations of motion, where the spinor field will depend on the scalar field, and likewise. So since they depend on each other, they are now interacting with each other. We can even have what are called self-interactions. So we can have the same old Klein-Gordon Lagrangian. We can add something that looks like this. We call this the phi-4 interaction. This term over here describes interactions with scalar particles. So now scalar particles can bounce off of other scalar particles. Now you guys might be wondering, isn't this over here already an interaction term? This is certainly something that I have always wondered. It turns out that it is, depending on how you define interaction. So it turns out that we can consider this entire term an interaction term, where the mass would be the interaction strength, or the coupling. But however, if we do this, the resulting particles still can't bounce off of each other. And we will see this in the next couple of videos. So we can still say that the mass of the particles arise because of the coupling with itself, because of the self-interaction here. But it doesn't really give us out things that we really associate with interactions. So we usually just call this entire Lagrangian the free Lagrangian. Though it is perfectly fine to call this an interaction term if we wish. It just depends on where you stop the line, if that makes sense. I'll talk about this more in the next couple of videos. So the answer to how twilight can explain rainbow dashes milk like increasing in temperature is that twilight will see rainbow dash interacting with a quantum field. And this interaction is going to cause a temperature. So that's how she will explain that temperature there. And we will actually be calculating this whole interaction from Twilight's view in the next series. I'll see you guys then. Thanks for watching and have a great day. Bye.